Here we go. Keep it still. Bobby Joe was absent yesterday, so this is for her. What we've got is the PowerPoint, and you got that. You picked it up, right, Bobby Joe?
No, I asked you where it was.
It's in the bin. It's always in the bin. Okay? Always. Oh, I thought you meant online.
No, I asked you.
Sorry.
We should put them online though, it's free.
I know, I'm thinking about it. Get that off your head. I don't want your lice. Okay? That's why you never share hats when you were little kids.
Black kids don't get lice.
Don't go.
Here we go. Here we go.
All right.
Yep.
They don't have flakes.
Here we go. Aqueous solution.
Ice is behind you.
All right, we're ready now. We're ready. Aqueous solutions. What we did yesterday is we saw the videos, and you would be able to draw Mickey Mouse dissolving a salt for me, right? Okay. Well, let's see. Let's see if you would have this. Okay. So, yeah, go ahead. This would be what I'm looking for on Monday's quiz.
He's laughing.
You can't draw a video, but you could certainly draw this. Okay? You would be able to draw for me a crystal lattice, and those crystals are made of ionic compounds, so we have a positive and negative ions being attached to each other. But when you throw that crystal of salt into water, you've got Mickey Mouse, and what happens is that the face of Mickey Mouse is it because it's slightly negative. How come? There's two lone pairs over there. Those lone pairs of electrons are going to attract a positive ion and tug it out of this lattice. In the meantime, Mickey's ears are going to tug at the negative ion in that solid and pull it out of solution. What we'll get then is we'll start to get cracks in the lattice. That's why you stir. So you can get those, you can shear off a few more of the ions and expose more of them to Mickey's ears or to Mickey's face. What will eventually happen is the water will surround all the negative ions by Mickey's ears, the slightly positive. And again, please label it, that's that funky delta positive being attracted towards negative ions. And all the positive ions will be attracted to Mickey's face, which again will be labeled delta negative. Delta negative. Okay? So that's how you're going to explain solvation or dissolution or hydration. On the next slide is what we called that. We said that water is polar, and we draw Mickey because that ear hydrogen, the face oxygen, that will help us dissolve our water, or our crystals, okay? So, we define solute, and again in our sample we just did, the salt would be the solute or solute, and the water would be the solvent, and that's what you answered for a few questions on the purple packet. We said water is a great solvent, but benzene is even better. Okay. What then we did is we defined molarity here because we're going to use it as we talk about a few other things, those things being acids and bases today. So molarity is defined as moles of solute per liters of solution. And the easy problems that you're doing on the textbook or on the purple packet are to solve for molarity if I give you a certain number of moles in a certain volume. So all you do is remember molarity is moles over liters, and then solve. You can use the big M, but I'll show you. You probably want to use this double label for molarity. Big M, okay? We're going to get to more of this today, okay? We're going to get to more of the mole diagram. The first couple problems will just be moving from moles to volume, but no 22.4. 22.4 is only for gases. Good. We're going to use molarity as a conversion factor, and then I'll show you most of our problems. We're going to solve for molarity. Most of our problems will use molarity as a conversion factor, every once in a while we'll actually use molarity as a given. Every once in a while. Okay, so I'm going to work these samples. I'll come back to this. Let's look at, because you need to pre-lab for tomorrow, these definitions. Okay? Now some of you had to help. Who did the carbon souffle demo? Okay, yeah, that everybody remembered too, Faith. In 4th hour, like, oh, Faith, we miss it. Okay, so Faith, you used what acid?
Where's she getting Faith? Who's in the class?
Oh, yes, Faith is here.
Oh, I didn't know she was in the class.
And Mang is new?
I'm new.
No, you used the other one, the acid. You used sulfuric acid. And she had the gloves and the goggles, right? And we wouldn't even let her touch it unless one of us was in the back room, because it's very concentrated. Very concentrated. I would never let you guys use that here in the lab. I would dilute it. And that's what we're going to do tomorrow. Actually what they helped me do is they took, my preppers helped me take concentrated hydrochloric acid is what you're using tomorrow. Now, concentrated hydrochloric, anybody know what's molarity?
18.
I've said it a couple times, kind of like that one question on the test. No, 3 is one of my stock.
1.
5.
What was it?
18.
18.
I said that right away.
Okay, I didn't hear. 18 molar. That means 18 moles per liter when I break out the concentrated hydrochloric. You, as Jack remembers, you use 3 a lot. 3 is diluted. How do I do that? That's what you're going. You're going to do those calculations for me. So 3 moles per liter versus 18 moles per liter, that's dilute. Now, I keep a pile, quite a few different acids, not locked up, underneath because they're my stock. We use them all the time. And Jack remembers 3. You remember any others, people that have helped back there? You didn't have to go in the lock cabinet. It was underneath for demos. Guesses? You used them a lot in Chem 1. What molarity was hydrochloric acid over there? 1. We have a large jug of 1 molar HCl, 1 mole per liter. And we've got quite a few 0.1s. You guys use a lot of 0.1s. Okay? So, dilute concentrated stock. That's how I showed you yesterday how I was taking my concentrated and adding it to water to dilute it. That's how we finished up making your acids yesterday. Okay? Now, this slide came next in your chapter. Now, those of you that read chapter 4, because I know you all did, right? Yeah, good. You went, well, I know this. Skip past. Oh, I had to answer a couple problems in the packet. Precipitation reactions. What? I can do those. We covered it in chapter 3. We really did cover acid-base in chapter 3 because it's a double replacement. Okay? So we did precip, we did that, but we didn't do oxidation reduction. So just a little heads up, our first test will be these. Our next test will get into redox, and that will be those types of equations. Now, the next slide, because we're going to chat a few seconds about precipitation reaction, because I've already covered them in chapter 3. You've already seen them. You're going to, you know that you have to use a solubility table. Oh no, not in college. They do not give you a solubility table. You need to memorize these. Now, I have tried very hard in Chem 1 and Chem 2 to make you know number 1. You know, don't even check the solubility table. All nitrates are aqueous, are soluble. You know, because we've done demos, sodium. I throw sodium in water, it dissolves. It explodes, and then it dissolves, right? The Brainiacs, alkaline metal, it dissolved, and then it explodes, which is why. But it certainly is soluble. Okay? You did the 1 lab. And you know that we can get those to dissolve. Okay, you used sodium chloride, you used sodium bromide, and the iodide, we used Ki. And that was liquid in that big lab, our big lab with our activity series. But you know that the one we always say to memorize is silver chloride doesn't dissolve. We said that one's always going to show up. Well, here's 2 more that you should memorize. Okay? Every time you do them, they don't. Now somebody was helping me make a little barium sulfate. That was a mess. Okay. Not going to dissolve. Had to do a few other things there. Not barium sulfate won't. Most other sulfates will. Hydroxide. You know we're going to use sodium hydroxide in a burette. That means it's aqueous. KOH, you pour it on your aluminum foil. That's aqueous. Okay? Some of these are slightly. So again, we're trying to get you experience as well as memorizing some facts. These other salts are slightly. We like charts, but again, you don't get charts. You got to memorize. You got to memorize with our charts. Okay?
Are you touching a student?
Have you ever seen Foster's Home for Imaginary Friends? It's just in my head right now and I can't stop laughing.
No. Here we go. Now, describing reactions in solutions. Oh my gosh. Do we really have to go back to chapter 3? Yes. Okay? No, we don't. Because how much more time do we want to spend? I know you can write this double replacement and you can make your silver chloride and sodium nitrate. What do I ask you to do? You know in chapter 3 all I ever said was balance and get me the net ionic. Some of you have to do this again as you start chapter 4 questions. You're going to have to break it all into ions, then cross out spectators, and then you're going to be asked for your net ionic. So you're going to bring down who's ever not left. Why is that still important? Because here's how your problems are going to read. If I have a 10th molar solution of silver nitrate and a 5 molar solution of silver chloride, and I'll give you the volumes, how many, here we go, in the net ionic, how many what ions are present at the end and what are in solution? Okay, what are in the precipitate? How many are left over? You're going, hey, that's going to be easy. Okay, so we're going to do a limiting and a reaction. So that's my goal, is to get to that one today. Again, sodium and nitrate are spectators. All right, Faith, could you just pop up and do a quick demo, and Tyler or Mackenzie, can you videotape her over here? She's going to put the goggles on. And I got 3 tubes. Let's use the empty one. Did you guys do this in Bio 2? The mummy lab? What? You every hour. Are you kidding me? I know. Well, that's it. Very careful, please. Okay? What Faith, in the old days, when we taught biology, when we teach biology, we would like to know, can I mix Bobby Joe's blood with Brock's?
Yeah.
Yep, maybe.
Okay?
Do Zoom or something?
And how I would be able to tell, in the old days, I'd have Bobby Joe do the little finger prick and squeeze a drop on a slide, and I'd have Brock do it, and then we'd mix them together with a toothpick, and if I would say, oh no, don't get his blood, if what?
DJ's
What would
head's in the way.
happen? They would, okay? Careful, the word you use in biology is agglutination. They would agglutinate, right? And what they would do is, fancy word for precipitate. What's going to be the problem if your blood cells precipitate or agglutinate? Why would you die? Huh? It won't work. They'll get too big. They'll plug up your capillaries, which will plug up your lungs, which will plug up your heart, which you will eventually. We did it with mummies. We pretended, and really it was chemicals. What 2 chemicals? Let's see if we can write this reaction. So squeeze generous amounts into the empty tube.
Is it playing right now?
I don't know.
How do you know if it's playing?
It's recording. It's been recording.
Which one is this?
The sodium iodide.
Sodium iodide.
This one?
Yep, and you can hold the tube up so they can see that it's nice and squirt another. Not very quantitative, pretty qualitative. So this was mummy number 1, and then we mix it with mummy number 2 and say, oh no. Actually, you can determine fraternities that way too. Nice clear solution. She's going to drop in another clear solution.
Silver nitrate.
Silver nitrate, again, it's clear. And prediction?
Oh, it's gonna react.
Okay, a little more would be good. Good job.
A lot more.
Okay. What happens?
Little excess fizzles, bubbles, anything.
No, what are we forming?
Precipitate.
Precipitate. Good. So, just a reminder of that. Just a reminder. See what we're away here. Nice job. Okay. Let's direct us back here.
Whoa. Hey, Val.
Get the camera.
I'm going. Yeah. With the strong acids. What are the strong acids? I told you this yesterday. HCl. Okay. NO3 because it's nitric. And sulfuric. How are you always going to remember them? Because you don't get charts. North High School. Good. Now, what does it really mean? What do they do? What they do, what a strong acid does, is completely dissociate. Hydrochloric and sulfuric and nitric are examples. I've got the chart on the next slide of a few more. Weak acids, on the other hand, do not. Now, weak acids, acetic acid, I eat that all the time. I don't eat hydrochloric. I eat acetic acid. Where?
Food.
And what foods?
Fruit chips.
Not so
Salad
much.
dressing.
You're thinking of citric acid. Where?
Salad dressing.
Salad dressing, right? Salad dressings have vinegar in them.
The benefit of
Vinegar is acetic acid. That's going to be your lab 22. You're going to titrate vinegar. You're going to tell me what it is. Where do you find formic acid? Another Bio 2 question.
Oh, Bio 2.
Canned foods.
Is it edible?
Give us a hint.
Toothpaste is tin 2 fluoride or fluoride. Nope. Formic acid?
What happened to electrolytes?
Bone marrow.
No.
Accurate.
Bees.
Oh.
Why does it sting?
It has formic acid.
They inject formic acid into you. And acids sting. Okay?
Is there like an acid strong enough to go through bone?
Oh, sure.
This one.
Oh, come on, Brock.
No, Brock. Brock, why do you need to know this?
I'm trying to hurt someone.
Let's say it involves a shovel, a guy, and my bathtub.
Are you?
I saw it
You saw it on you watched that, what is it, Decker? What's it?
It's either Criminal Minds.
Yeah, Criminal Minds. Yeah. Criminal Minds
In the
is where
bathtub with a shovel.
Okay. Strong bases, we're going to use the strong base tomorrow, however it's going to be dilute. Strong base, but dilute. Okay? What happens with them? They completely ionize. Now, weak bases do not. What does all this mean? Let's really look at this, and that's what we've got here is...
Oh, come on.
Strong acids.
Hydrochloric acid is a strong acid. The compound hydrogen chloride ionizes completely, so many ions are free in the solution.
Now that's what you guys did for your first purple sheet. You totally broke everybody into ions. That's not the case with a weak acid.
Hydrofluoric acid is a weak
Breaks
acid
apart?
because it
Oh,
only
comes back.
partially
Breaks
ionizes.
apart?
At any
Comes
one
back.
moment, most of the HF molecules have not split into their ions.
All right, and since we're here, let's watch. Base is going to be the same thing. Strong base,
NaOH,
Completely
sodium
ionized.
hydroxide, is a strong base because it dissociates completely. In aqueous solution, it breaks into sodium cations and hydroxide anions.
okay? So completely dissociates. Weak
Left
base,
is H2O, water. On the right is NH3, ammonia. The dots and lines represent electrons. Ammonia acts as a base in water. It removes a hydrogen ion from water to create hydroxide and ammonium ions. In solutions, only a few hydroxide ions are created at any one time.
okay?
So ammonia is a weak base.
So back to the PowerPoint, because some of you missed it. Okay?